Hello, this is Professor Keen, and welcome back to Electricity, Magnetism, and Light, lectures at Wisconsin Lutheran College. Right now we're talking about Chapter 11 of A Student's Guide to the Great Physics Texts, Volume 3. This chapter is titled The Conservation of Energy. In my last lecture, I read through the introduction which sets the stage for this chapter and does some review of the previous lectures. Now I want to ask this question. If heat can produce mechanical power, why and how does it do so? And maybe to set the stage and to provide an example of the kinds of things that Helmholtz is going to be talking about, I'd like to introduce you to the concept of a steam engine. So let's suppose, so here's the question. How can heat accomplish work? That is the general question that is being asked at the outset of this chapter. So consider the case of a steam engine. Suppose that we have a metal chamber, and in this chamber there's a pipe coming out one side of it, and there's a valve that can be opened and closed. And in this chamber there is water. This valve is connected to another pipe, and that pipe is connected to a piston. So this is a chamber which contains a tightly fitting piston like this, and that piston is attached via some kind of joint to a rod, and this rod is attached to a wheel. Specifically, it's attached to the perimeter of this wheel, and this wheel can turn. I'll explain how this works in a moment. This chamber in which the piston is sitting is attached to another valve, and that valve is attached to a third chamber. Okay? Now, here is the idea. This chamber over here has built underneath it a fire. I'm just going to draw some logs here. This could be coal or some other means of generating fire. So I'll draw a little fire right here. Okay, that is able to heat up the water that is in this chamber. And when that is heated up, it produces steam. This chamber over here we'll refer to as the boiler. Now, when that fire is lit and steam is produced, the pressure in that chamber increases. And then, by opening this valve right here, one can allow the steam into this chamber containing the piston. And as long as the valve on the right side of this chamber is closed, the pressure in this chamber increases, pushing the piston upward. When that piston is pushed upward, it turns the wheel, and work can be produced. So work is performed when this piston is pushed upward. You might imagine this wheel turning, and this could move, this could lift a weight, or it could move an engine and turn wheels. Okay, so this piston is pushed upward, and then at the moment that it's at the top of its stroke, suppose we were to close the valve on the left and open the valve on the right. When the valve on the right is opened, the steam enters this chamber right here. And now suppose that beneath the chamber on the right, we put some blocks of ice. I'll draw some ice cubes over here to schematically represent this situation. And this hot steam, when coming into contact with this cold walls of this chamber, will then condense, forming droplets which rain down and form water in this chamber. This chamber on the right hand side we can refer to as the condenser. And then as this vapor, this steam, turns back into water, the pressure drops, and the pressure in the central chamber drops, and then the piston goes back down, which continues to turn the wheel. Then you might imagine this collected water can be drained out of this chamber and fed back around into the chamber on the left via some kind of drain and maybe a pump of some sort. You might even use some of the energy of the work done by the expanding piston in the middle to drive a pump that pumps this water back around in this direction, and then you repeat the cycle once again. So by boiling the water on the left and appropriately opening and closing the valves and condensing the steam on the right, one can imagine performing a cycle of work, pushing this piston up, pulling it back down, pushing it up again, and pulling it back down. The question is, how much work can be done by a certain quantity of heat? So this is the second question I want to ask, is how much work can this engine perform? And in particular, how much work can be done by a given quantity of heat that one is generating? And for that matter, and here's a third question, what do we mean by heat? So what do we mean by the term heat? If we are going to claim that heat can accomplish work, and the steam engine is an example of this, then what do we mean by the term heat? So what I want to do is review, along with Helmholtz, the old theory of heat, which is called the caloric theory of heat, and then the new theory of heat, which is called the mechanical theory of heat. So first of all, by way of review, the old theory of heat which is also called the caloric theory. This is the theory that had been inherited by people in the 1800s. What is the caloric theory of heat, or this old theory of heat? Well, it said that heat is essentially an invisible and imponderable or very light substance. So heat is an invisible and imponderable, is how Helmholtz describes it, weightless, imponderable, or weightless substance. That's the basic axiom of this, that heat is an invisible substance. When this heat flows into a body, it causes its temperature to rise. When heat, and by the way, this fluid is called caloric, that's why it's called the caloric theory of heat. When this heat, or caloric, flows into a body, it causes the temperature of the body to rise. That's the idea. So in this way, the presence of heat is manifested or shown as a rise in temperature. On the other hand, when heat leaves a body, its temperature falls. That is the idea behind this caloric theory of heat. Importantly, heat cannot be created, according to this theory, or destroyed. It is an invincible substance that simply goes from one place to another. And although it cannot be created or destroyed, it can be hidden. What do we mean by that? Why would we think that it can be hidden? Well, in some cases, heat can flow into a body, but the temperature does not rise. Heat, or caloric, can flow into a body, yet the temperature does not rise, or the temperature does not increase. In that case, the heat that flowed into it is said to be latent or hidden heat. The heat is, in this case, latent heat or hidden heat. Remember, we said that heat is manifested or shown typically when it flows into something and the temperature of that body rises. That would be manifest heat. But if heat flows into something and the temperature does not go up, then that heat must be latent or hidden. When does this happen? Well, it happens in the exact situation that I described above. So, for example, when you have heat flowing into ice, what happens if you have ice at 0 degrees Celsius? The heat flows into it. Does the temperature of the ice rise? Well, no. What happens is the ice melts. The ice melts into water, but the water is at 0 degrees Celsius. So you have heat flowing into something, and it causes a change in phase. The ice goes into water, but the temperature of the water is the same as the temperature of the ice, that the ice had been at 0 degrees Celsius. So you imagine sort of this heat going into the ice, melting it, but the temperature stays the same. So what is said to be the case, according to the caloric theory of heat, is that the water contains latent or hidden heat. Latent heat. And of course, when that water turns back into ice for some reason, it gives up that latent or hidden heat. That is the caloric theory of heat. In fact, many of the scientists who developed the theory of thermodynamics, that is the study of heat, they completely and fully believed in the caloric theory of heat. So next time, I think I'm out of space, so why don't I pause here and I'll talk specifically about Sadi Carnot, he was one of the architects of the modern science of thermodynamics, and he believed entirely that heat was an indestructible, invisible substance, this caloric. And interestingly, maybe I'll mention this right now before I stop, is that even today, people who do not believe in the caloric theory of heat, which I would say is most scientists, they still use language that was developed by those who did believe in the caloric theory of heat. Think about it. We talk about heat flowing from one place to another as if it was some kind of fluid.